In this video, we're going to cover section 1.14, the Lindemann mechanism. The Lindemann mechanism for unimolecular reactions provides a good example of the relationship between kinetics and reaction mechanisms. This mechanism was developed to describe the observed concentration dependence in unimolecular dissociation reactions of the form where you have a single reactant which then fragments into products. In this reaction, a reactant molecule undergoes decomposition when it acquires a sufficient amount of vibrational energy. So the question we ask ourselves is, how does the reactant acquire sufficient energy to undergo decomposition? Well, one possibility is that the reactant acquires sufficient energy to react through a bimolecular collision. Experimentally, however, the rate of decomposition demonstrates only first-order behavior at high reactant concentrations and not second order, as expected for a single-step bimolecular mechanism. Lindemann proposed another mechanism to explain the order dependence of the reaction with respect to reactant concentration. So we're going to look at that today. So the Lindemann mechanism involves two steps. First, reactants acquire sufficient energy to undergo reaction through a bimolecular collision. As shown, we have two molecules of A that are going to collide to give us A star plus A. In this reaction, A star is the activated reactant that has received sufficient energy to undergo decomposition. The collisional partner of the activated reactant molecule leaves the collision with insufficient energy to decompose. So this is the only reactive species resulting from that bimolecular collision. In the second step of the Lindemann mechanism, the activated reactant undergoes one of two reactions: collision resulting in deactivation or decomposition resulting in product formation. So the first, we have the activated reactant colliding with another molecule of A, which in effect deactivates back to simply 2A molecules. The other path is the activated reactant molecule decomposes to product. And overall, it's the separation of the reaction into two steps, which is the key conceptual contribution of the Lindemann mechanism. Specifically, the mechanism implies that a separation in time scale exists between activation and deactivation product formation. So here we have a figure representing the Lindemann mechanism. Above, we have the elementary reaction steps of the mechanism, and described below are two molecules of A colliding through a bimolecular collision to give us our activated reactant A star. And then subsequently, A star will undergo one of two possibilities. It will collide with an unreactive A molecule to give us back the deactivated state, or it will undergo decomposition to form new products. So as shown, the only process resulting in product formation is the final decomposition step. Therefore, the rate of product formation can be written as follows, where it is equal to the rate constant K2 and dependent upon the concentration of the activated reactant. Similar to what we've seen with our steady state approximation questions, where we are trying to devise a rate law expression for a complex reaction mechanism, we'll apply the same sort of process here. So the next step is to develop an expression for the concentration of that activated reactant in terms of the reactant concentration A. This is required because the activated reactant A star is an intermediate species. The relationship between the concentration of A star and the concentration of A is obtained by writing the differential rate expression for the concentration of A star, and then applying the steady state approximation to it. As shown, we can write an expression for the rate of formation of the activated reactant, and you can see that there are three terms present in this expression because A star is present in each of the three elementary steps of the reaction mechanism. Now we can apply the steady state approximation to this time derivative because A star is a reaction intermediate. As a result, we're going to equate this expression to 0. And finally, we can substitute this quotient into our original expression for the rate of product formation such that we're left with our final rate law expression for product formation according to the Lindemann mechanism. So now let's look at how the concentration of the reactant can affect the order dependence of the reaction. This is the key result of the Lindemann mechanism. It states that the observed order dependence on the concentration of A depends on the relative magnitude of these two terms. So we're comparing the product of the rate constant K minus 1 times the concentration of A to that of the magnitude of K2. At high reactant concentrations, the following condition will hold, where the product of the reactant concentration in K minus 1 will be much greater in magnitude than that of the rate constant K2. As a result, we're going to see this term drop off and a cancellation of the concentration of A into the numerator. And that's going to lead us with the following expression for product formation. This demonstrates that at high reactant concentrations or pressures, the rate of product formation will be first order in the concentration of A, consistent with experiment. Mechanistically, at high pressures, activated molecules will be produced faster when decomposition occurs, such that the rate of decomposition is the rate determining step in product formation. However, at low reactant concentrations, the condition is different. It's reversed, where now the magnitude of K2 is much greater than the magnitude of the product of K minus 1 and the concentration of A. So in this scenario, the rate law expression reduces to the following, in which now the rate of product formation is only dependent upon the rate constant K1 and to a square or second order with respect to the concentration of A. This demonstrates that at low pressures or low concentrations of the reactant, the formation of the activated complex becomes the rate determining step in the reaction, and the rate of product formation is second order in A. So overall, the Lindemann mechanism provides a nice example for unimolecular dissociation reactions, which shows that there is a strong dependence on concentration of the reactant with the order dependence of the reaction. So if you have any questions about the Lindemann mechanism, by all means, send me an email. Thank you.